So, in terms of your research into quantum gravity, uh, what is the sort of parallel challenge or the parallel path you're trying to take to make progress?
Okay, so Einstein, as I said, started with this equivalence principle, and so the idea is that perhaps there is a quantum equivalence principle that can play a similar role in constructing a theory of quantum gravity that the equivalence principle played in constructing the theory of general relativity. And so I should try to explain the quantum equivalence principle, but to do that, I kind of need to back up a bit. So if you're asking the question of how do I combine general relativity and quantum theory, well, you should look at these two theories and ask, what kind of theories are they? And they have, they each have conservative and radical features. So general relativity is conservative in that it's deterministic. It's a classical theory.
By conservative, do you just mean that it's similar to other theories that came before it?
Similar to, yes, theories in the past, yeah. Yeah, I think that's what I mean. Yeah, it's not surprising in some sense. And perhaps it's not surprising because of that similarity. So it's conservative in that sense, that it's deterministic. But it's radical in that the causal structure is dynamically influenced by the distribution of matter. So the causal structure is the pattern of before and after. Events are before other events. There's this pattern of events that are before and after each other, and that pattern is influenced by the curvature of space-time. So if matter affects the curvature of space-time, then matter affects the causal structure, and so that's radically different from Newtonian physics, for example, where time was regarded as this absolute structure in the background. Time just evolved, unaffected by anything else. So dynamical causal structure is this radical element from general relativity. And now if you look at quantum theory, well, it also has radical and conservative elements. The conservative element is that the causal structure is fixed. It's just like Newtonian causal structure. It's fixed. It's in the background. It doesn't change. And the radical element is that it has this property, I would call it indefiniteness. So a particle, if it can go along one of two paths, it actually goes along both paths at once. It doesn't go along a definite path. So it's indefinite as to which path it goes along. So I call that indefiniteness. So if you take those two radical properties together, and if you believe a theory of quantum gravity has to follow the radical path in both cases, then you expect a theory of quantum gravity to have indefinite causal structure. The causal structure will not just be something that varies, that changes, but also there will be two different causal structures at the same time, in some sense. Same time is the wrong word, but two different causal structures will both be pertinent, both hold. So so that's, I think, the sort of the central property we're likely to have in a theory of quantum gravity. And that's a really strange idea. The idea that if you have two events, usually you think, well, one event is before the other event. Event A is before event B. But here you could have it being true that event A is before event B, and also event A is after event B. Both of those things would be true, not just one of them. So you'd have indefiniteness as to the causal structure. And that is not something we're used to. We're not used to thinking about the world in those terms. So the question is, how do you make sense of that? How do you do physics still when you have something like that? And so the idea is to look at what Einstein did with the equivalence principle. And what he did was he said, well, you may have behavior which is, let's see, like non-inertial. So it looks like things are moving in curved lines. It looks like things are behaving in a weird way. But you can always transform into a frame of reference where you just have objects moving in straight lines, where Newton's laws apply, where things are just moving in straight lines, and that's called inertial behavior. So, and the way you do that is just by looking at it in a frame of reference that's falling, and then, at least for a short while, locally, things will be moving in a straight line. So a different way of understanding what Einstein did with the equivalence principle is to say that the equivalence principle says that there always exists a frame of reference with respect to which the behavior is inertial in a small vicinity around any point. Okay, so this is something he did. And now the question is, can we take that principle forward to the problem of quantum gravity? And the idea is to draw an analogy between inertial behavior and definite causal structure on the one hand, and non-inertial behavior and indefinite causal structure. Because in general relativity, non-inertial behavior is the sort of the weird thing that you're trying to tame by going to a falling frame of reference. Mm-hmm. In quantum gravity, indefinite causal structure is the weird thing that you're trying to tame. So that's the sort of background. And now, what would the principle say? Well, the principle would say, can you find a sort of frame of reference where you get rid of indefinite causal structure, at least locally in a small region? Mm-hmm. Well, that's not quite enough. What you need to do is find what's called a quantum frame of reference. And this is a subject that was developed many years ago by Yakira Haranov and other people, quantum frames of reference. And it turns out you can do this. So what you can do is you can find a quantum frame of reference, a quantum coordinate system to measure that frame of reference, where locally, in the vicinity of a small point, you get rid of indefinite causal structure. The causal structure becomes definite.
So you know that A causes B?
Yeah, you know that A causes B. Now, what you do when you impose that, you try to make it work in a small region, and then everywhere else it goes haywire. Mm-hmm. But that's okay, because you can hope to use the tricks that Einstein used in general relativity. Mm-hmm. In his case, he knew he could locally make everything inertial, and if he did that, further away from there, it would kind of go haywire, mm-hmm. Crazy non-inertial behavior. But that's okay, because he could write down some equations at that point that worked. And so the hope is to be able to do the same trick in quantum gravity.
Is it especially difficult because you're dealing with these more radical, what's the other word?
Non-conservative?
Non-conservative element? Is there more uncertainty or just probabilities as opposed to certainties?
Yeah, so I mean, a different approach would be to say, well, no, I'm going to take the more conservative path in each case. I'm going to look for a theory which is deterministic and has fixed causal structure. It just seems unlikely to me that would work. I mean, it's not completely impossible. Maybe you could find some theory that was in some sense more classical, more like older theories where that worked. And there are even ideas that I think fit into that category. But it seems to me to be the wrong idea. One should embrace the radical elements and see how to go forward.
And is that what's really unique about your approach to quantum gravity? Is that what sets your approach apart from other approaches?
So definitely it's true that my approach is to put this indefinite causal structure front and central. I think this is the central conceptual problem, and then we work out from that. Other approaches, insofar as I understand them, are not doing that. But everyone has their own take on this. So I think what's important when it comes to solving problems like the problem of quantum gravity is that there are many different approaches. So pluralism is essential in physics, as it is in other walks of life. And so I'm hoping to bring a different kind of approach. I mean, there are other people now thinking about indefinite causal structure and quantum gravity. So I'm hoping there's starting to be a bit of a community.
And it's basically 100-year-old problem, more so, in terms of marrying these mm-hmm. theories. Is that challenging for a researcher to be working on a problem that has, pass through other researchers' careers without being solved?
Yeah,
Do you
well-
foresee a day when you say, well, you or a colleague says, "Oh, yes, that's quantum gravity. We've done it."
I mean, I think we can do it. I mean, there are. I don't know that the particular approach I'm taking is the right one, and you know, it may well not be the right one. There could be some young physicist at the moment who has the right idea, or somebody who's yet to even enter the field of physics. Typically, big breakthroughs are made by young people in physics, and so that's really where the hope lies.
And what would it mean if it were, maybe you haven't even thought about that, but if these big questions had a solution, if the new theory, the unifying theory was found, what would that mean for physics? Would physics be done and we can all go home?
Yeah. Again, it really depends on what the answer is, doesn't it? I don't know. People were thinking about electricity and magnetism, and people started to become aware that there's electric. You started sending electricity through wires, and people had magnets wherever. And I don't know if people before the subject was really completed by Maxwell, I don't know if people really understood what it would mean. What it would mean to have Maxwell's equations written out. And Maxwell's equations have had a tremendous impact on humanity. So much of our technology relies on understanding electricity and magnetism. And conceptually, I'm not sure if people anticipated that this would lead to problems with relative motion. How would the speed of light would become a point of interest. There's problems come up when you get an answer, when you start to get a theory, and you can't really anticipate that in advance. So who knows? When someone comes up with the theory of quantum gravity, I think we'll be surprised by it. I think it'll be interesting, and I think it will lead to questions that we can't possibly anticipate at this stage.